Hi, I'm Kenny. I'm a software engineer at Facebook, and today I'm going to talk about deadlocks. So before I start, I want to tell you a story. So several years ago now, I had just joined Facebook, excited to work on large distributed systems. I was doing my first production release, and then I had just pushed to a subset of production. So almost immediately, we got reports that requests to our service were failing. But our monitoring, all our health checks said our service was alive and running. So what's going on? We core dumped the process and started debugging for a bit. And we soon realized we had a textbook deadlock. 2 threads, 2 mutexes waiting on a cycle. We fixed that issue and then started another push. Another deadlock. And we fixed that one too and started another release. Another deadlock. So eventually we fixed all the known deadlocks and finished the release. So that's 3 deadlocks, my first production release. Welcome to C++. So this experience traumatized me so much that since then, I pledged to myself to fight the good fight against deadlocks. And I have this little Hulk on my desk to remind me of this. So me being naive, I thought, how is this even an issue? I thought deadlocks were a solved problem. You put an order on the locks, acquire them in that order, done. I soon realized it wasn't as simple as that. There must be some tools we can use to make deadlocks a non-issue. And this is what this talk is about. So in this talk, I'll explain why deadlocks are hard to debug at our scale. And then I'll explain what I mean by end-to-end and how our tools fit into this picture. And then I'll also do a deep dive in each of these tools. In order to understand why deadlocks are difficult to debug, I need to provide some context on how we use C++ at Facebook. So just a note about memes. Originally, my presentation had lots of actual memes. But our legal team told me I had to remove all of them. Couldn't keep a single one. And the reason for this is because we don't own the rights to the original source images. OK. But all original content is OK. So I improvised and came up with a solution to my legal problem. I drew my own memes. So any resemblance, coincidence. So back to C++ at Facebook. Almost all of our C++ is contained inside a single monolithic repo. It's very large code base, very complex. If you work on C++ at Facebook, you are probably responsible for a back-end service, things like messaging and ads. So how do deadlocks relate to all of this? So as in my story from before, deadlocks are especially worrisome because the service may appear alive but is failing requests. Some threads could be deadlocked while some other threads still make progress. Detecting deadlocks can also be very difficult because reproducing the exact environment, the exact request, and the timing can be very difficult. And so it can be very hard to reproduce in a test environment. It's also very easy to introduce deadlocks accidentally during development. So recall, in order to have a deadlock, you need a cycle in the waits for graph. We typically avoid deadlocks by assigning an order to the mutexes and acquiring them in that order. But this knowledge is typically encoded at most in comments in source code, if at all. There is no tooling to actually enforce this logic. And then lastly, the threads and mutexes involved in a deadlock might be split across multiple files, projects, and multiple levels of indirection through inheritance or callbacks. So it can be very difficult for a human to make sense of all of this. So hopefully I've convinced you that debugging deadlocks is difficult. What can we do? And for the rest of this talk, I'm going to address this problem. What tools can we use to make detecting, debugging, and preventing deadlocks easier? In order to understand our approach, I'll explain to you what I mean by end-to-end at Facebook. First, there's an observation. At Facebook, service developers are responsible for all phases of the service lifecycle. The typical life of a service is as follows. Engineers will develop and test new features and then land your changes upstream. Then it's time to release the service, and you cut a release candidate, and you push the service to production, typically in phases. Once your changes have been rolled out to all of production, you want to monitor your service to make sure there's nothing wrong with your service. When we think of monitoring, we typically think of CPU, memory, and other service-specific counters. Inevitably, your service will crash or experience some anomalous behavior, and then engineers will need to debug this, fix the bug, and then the cycle repeats. To make deadlocks easier to debug, our approach is to develop end-to-end tooling to help engineers detect deadlocks in all of these phases. By applying these tools end-to-end, engineers will have higher confidence in deadlock-free code. And note, the tools I'm about to show you are all open source, and I'll reference this at the end for you to go to them. So let's start talking about these tools. First, I'll tackle the problem: how can we prevent deadlocks during development and testing? If we can prevent deadlocks here, then we're done. This is the best possible place. There's no impact to production. First, an observation. Most of the deadlocks I have observed in production are typically caused by overlocking. Here's what I mean by overlocking. Originally, you start a new project. Your class is super simple. You have a single mutex called mutex and a few data members. Over time, engineers add more stuff to this class. Business needs change, teams change, the class grows in complexity. Eventually, no one really knows what the mutex is supposed to protect. So just to be safe, to avoid data races, we always hold the mutex. Critical sections start blowing up. Eventually, from a critical section, we call some other function that acquires some other resource, and then this results in a deadlock. If we can avoid this overlocking problem, we can reduce the risk of deadlocks. And our approach here is to use folly synchronized. Folly is Facebook's open source C++ library, and Synchronized is one of the components inside this library. Synchronized encapsulates a mutex with the data it protects. So it's impossible to access the data without acquiring the mutex first. Note that Synchronized is just syntactic sugar. Whatever you already do with mutexes or shared mutexes, this does not add any new overhead. So here's an example. The red lines here are the critical sections. Say you're implementing a class that kept track of a counter, so think atomic counter. But also you want to keep track of the history of the deltas that brought the counter to that state. The simplest way you might implement this class is to have a single mutex, maybe a shared mutex, an integer representing the count, and a vector of integers representing the deltas. OK, so what if a new engineer comes along and adds a new data member here? Should we lock the mutex? Should we hold the mutex when touching that field? Should we not hold the mutex? There's nothing actually in the programmer's original intent is that the mutex should always be acquired when mutating or reading counter and deltas. But there's nothing actually enforcing that intent. And then when you add a new member to the class, no one really knows anymore. What if we call our function here? It is very easy to forget to close the scope of the unique lock. And now we unintentionally hold the mutex while calling another function. Now let's rewrite this class with folly synchronized. The code looks almost exactly the same, except the red code is now green and inside of a lambda. Synchronized allows us to encode the programmer's intent into the type. The synchronized declaration, state underscore, means if I am state underscore, I protect capital S state and all of its guts. And you can optionally pass me a second parameter type, and I'll use that mutex type to protect it. And the only way for you to access capital S state is to go through me first. And I'm going to make sure you hold that mutex when you read or write the data. Now, there's no way for you to access the data otherwise, except to go through the synchronized data structure. So now if a new engineer comes along and they see this, they're going to think twice. Should I add my new data member to capital S state or not? Does it require synchronization or not? And same with a new function call. They're going to think twice. Should I add it inside that lambda or not? Does it require synchronization or not? OK, so using synchronized is one approach to reduce the overlocking problem. Our next approach for development testing is to run all our tests with ThreadSanitizer, or TSAN. TSAN is part of the larger Sanitizer suite open sourced by Google. The Sanitizer suite adds compiler time instrumentation to your binaries to find bugs at runtime. For the case of TSAN, it instruments all memory accesses and mutex calls. And it can find data races, lock conversions, and other types of synchronization bugs at runtime. The important thing to note with TSAN is that it's a dynamic analysis tool. So the higher the code coverage, the more useful TSAN will be. And we'll come back to this fact later. So every time an engineer at Facebook sends a change for review, our continuous integration system will build and run all affected tests in all different build modes, including sanitizers. So I happen to work on a project called Tupperware, And each of these lines represent different build modes of my project, and all tests have passed in those different build modes. And the one in red is TSAN, or ThreadSanitizer. Engineers will wait for all the builds and tests to land before landing their changes, and this will help prevent new regressions in trunk. So now it's time to release our service to production. Perhaps our test coverage wasn't comprehensive enough for TSAN to have value, and it was too difficult to refactor our code to use a new synchronization library. What can we do now? How can we detect deadlocks before we release it to all of production? So recall from a few slides ago, the higher the code coverage, the more useful TSAN will be. Tests only exercise a limited set of production code paths. If we could exercise more production code paths, TSAN would help us find more bugs, including lock inversions. So why don't we actually run release candidates with TSAN? So to do this, we build our release candidates with ThreadSanitizer and then push to a subset of production. The goal here is to exercise real production code paths. And then we either send a subset of production traffic or shadow traffic, and I'll explain what that means in a moment. We then monitor these TSAN replicas of our builds, and if things look good, there are no crashes, no deadlocks, we can proceed with the wider rollout of the normal optimized production build. So here's how this works. For most services, there's typically some load balancer to spread traffic across the multiple replicas of my service. We push TSAN builds out to a few of those replicas, and then we either send a subset of real production traffic or shadow traffic. And for shadow traffic, we record and replay old production requests, resend them to the TSAN replicas, and then ignore the responses. The only purpose of this is to get the TSAN replicas to execute the code they would otherwise be running had they been running a normal production binary. We've used this technique on several services at Facebook and found real deadlocks in production. So for this particular deadlock, we had a deadlock with 6 mutexes. And there's no way a human could have found this by hand. It was split across so many different files and directions, callbacks, inheritance. And there's no way our testing could have caught this because in order to trigger this code, it relied on production data. OK, so now we've released our service to production. Perhaps it was too difficult to set up TSAN builds with production traffic or shadow traffic, or we're still paranoid we might have deadlocks. How can we monitor for deadlocks in a running production service? Can we come up with a tool for this? We have the additional constraints here that if we do have a tool for this, we don't want to have to restart our service to use it. We don't want to cause additional downtime. We also don't want to have to recompile our binary in a special way because we're typically running normal production builds. We want our tool to work on normal production builds. Our approach here is to use Linux BPF. I'll explain what Linux BPF is in a few moments. We built a Deadlock Detector tool using Linux BPF, and it will find lock inversions on pthread mutexes and anything that uses that underneath, so standard mutex. This tool runs alongside the binary, and you can turn the tool on and off. It does not require a process restart of the process you're tracing, and you don't need to recompile your binary in a special way to use the tool. So the way we use the tool is we periodically run the tool on a subset of production machines. So let's say every 15 minutes or so. And if it finds a deadlock, we log it. Otherwise, all is good. So let me show you an example of the tool in action. Here's a small program on the left. There's 3 mutexes, 3 threads. Each thread acquires 2 mutexes, and collectively they acquire the mutexes in a cyclical order. Note that deadlock is not possible in this program because each thread is joined before the next one begins. But had we moved the join clause to the bottom of the function, then deadlock would be possible. But in this case, we still want to know that there's a lock inversion in this program. Now imagine that we have a running production service. It's calling this code. How can we find a potential deadlock? Our tool, if you pass it a process ID, will find this lock inversion. If while the tool is running, the service hits this code, the tool is going to output this on the right. It's going to output the mutexes and the threads involved with the lock inversion, as well as where each mutex was acquired by which thread. And the output here is very similar to TSAN. So how does it work? To understand how the tool works, I need to explain to you briefly about how BPF works. BPF, or eBPF, stands for Extended Berkeley Packet Filter. Originally, BPF was developed for finer grained control over networking, like controlling packets. But now it's become a full-fledged virtual machine-like thing inside the Linux kernel. The user can provide arbitrary code to execute at various hooks inside the kernel in a safe and efficient manner. So these hooks include any kernel space symbol, any user space symbol, like pthread mutex lock, and other types of trace points. And within our custom code, we can compute calculations and export these data structures back to user space. So let's see how all of this fits together. The green box is the trace process that we would like to find deadlocks in. It's running on top of the Linux kernel. And inside the Linux kernel, there is the BPF virtual machine. Our tool will register hooks inside of the BPF virtual machine so that whenever our trace process hits pthread mutex lock or unlock, it's going to trap into the kernel. Since we registered our custom code, now our custom code is going to execute, compute some calculations, which I'll go over in a few moments, and then export these shared data structures back to user space. Our tool will then use these calculations to build the waits for graph. And if there's a cycle in that graph, it indicates a lock inversion in the green process, in the trace process. So what happens in our custom hooks for pthread mutex lock and unlock? I'll explain it by stepping through a program. So first, the data structures on the right, these are the data structures we're exporting from the kernel to user space. For each thread, we maintain a list of mutexes currently locked by that thread. And then we also maintain a separate list of edges, which I'll explain in a moment. So thread 1 acquires mutex 1. We add it to our list. Then while holding mutex 1, thread 1 acquires mutex 2. As a result, we add the edge M1 to M2 into our graph. In this graph, nodes are mutexes, and an edge from A to B indicates that there is some thread where while mutex A was locked, we try to acquire mutex B. So in this case, we're sort of holding A, waiting on B. Now thread 1 unlocks all its mutexes and we proceed. So some of you might be wondering, why don't we delete edges? The trick to preventing deadlocks relies on consistent lock ordering. More edges might be added in the future, and by keeping around the edges, we can detect any inconsistent lock ordering now or in the future. So that's why we don't delete edges. Now the same thing happens for thread 2. It acquires mutex 2, and while holding mutex 2, we acquire mutex 3. So we add that edge. And now it drops all its mutexes. And now thread 3 acquires mutex 3. And while holding mutex 3, it acquires mutex 1. So now we have a cycle in our graph. And a cycle in this graph indicates a lock inversion or potential deadlock in my running process. Now suppose we did all our due diligence from all the previous phases. We rewrote our library, we're using TSAN, we're using monitoring. But we still get a crash. We still get a hung process, or we get a core dump from a deadlocked process. So how can we detect deadlocks in our service after it's already deadlocked or crashed? Our approach here is to use a GDB extension to analyze mutex internals. So we chose to use a GDB extension because that's already what engineers at Facebook are using whenever they debug a process or a core dump. So by adding a new command, this can help engineers be more efficient. Our GDB extension introduces a new deadlock command. And when you run that command, if there is a deadlock in your process, then it will output all the threads and mutexes involved in the deadlock. Here's some example output. Here we have a running process that's been deadlocked. We attach GDB to it, and the GDB has loaded our extension. We type deadlock, and now we get all the threads and mutexes involved in the deadlock. And the picture on the right visualizes this waits for information. In this case, unlike the BPF tool, the nodes here represent threads, and whereas for the BPF tool, the nodes represented mutexes. So in this graph, nodes are threads, and an edge from A to B indicates that thread A is currently waiting on a mutex held by thread B. So how does the GDB extension work? First, our tool will find all the threads that are currently stuck in pthread mutex lock. Then for each of those stuck threads, we examine the internals of the mutex we're waiting on. In the nptl, or native POSIX thread library, implementation of pthread mutex, the mutex keeps track of the thread ID that currently owns the mutex. So by using this owner information, we can find a thread that we are blocked on. So in this case, thread 3 is waiting on a mutex currently held by thread 4. So we construct this edge, and then we do this for all the threads, block threads in our program, and a cycle in this graph indicates a deadlock in the process. Now let's recap. I've just walked you through multiple debugging tools at Facebook and how we use it in each of the phases of the service lifecycle. Here's how they all fit together. For catching deadlocks during development, we can use folly synchronized and run our tests with ThreadSanitizer. ThreadSanitizer is more useful as it executes more code. So we run our binaries with tsan on a subset of production. Once we release our service to all of production, we can still monitor for the presence or potential deadlocks using our BPF tool. And then when our service has actually crashed, we can quickly find a deadlock using our GDB extension. The result of this work is that for many services at Facebook, our tools have helped us catch many existing deadlocks in production and have helped prevent new deadlocks from being introduced. So you might be wondering, what are the pros and cons of each tool? There are multiple dimensions to consider. So the first is, do we need to rewrite our source code to use it? Folly Synchronized is the only library here, and that's the only one that you would actually need to change your source code to use. Do I need to recompile my service to use the tool? So folly Synchronized is a library, so yes, you do. tsan, you don't need to change your source code, but you do need to recompile your binary in a special way to use it. The other two tools do not. Can I use the tool in a dead process? So by here, a dead process, I mean a core dump. So the other tools except for GDB require the process to actually be alive. But for GDB, if you pass a core dump, it can still find a deadlock there. So what's the overhead? So there's no overhead for folly synchronized in our GDB extension if you're already using mutexes. There is a big overhead using tsan in terms of memory and CPU. There is also an even bigger overhead using our BPF tool. But the nice thing is there's no overhead if our tool is not running. So it's a trade-off. What types of mutexes do our tools work for? So for folly synchronized, anything that implements the normal lockable and shared lockable traits will work. You can pass that as a second template parameter. For ThreadSanitizer, all the normal mutexes will work, and you can also instrument your own custom mutexes. And the last tool, our BPF and our GDB tool, will only work for pthread mutexes and things that use it underneath, like standard mutex. And then finally, what kinds of bugs can it catch? Folly synchronized is meant to prevent deadlocks. It's meant to prevent data races, but its API encourages smaller critical sections, thereby reducing risk of deadlocks. tsan can find many types of synchronization bugs, so you get the most bang for your buck there. Our BPF tool can detect lock inversions or potential deadlocks in a running process, and our GDB tool can actually find you the deadlock if one occurs. So these are the tools we've developed. What other things did we try and not work? So all these tools most of these tools I've mentioned are runtime analyses. You might be wondering, have we tried static analysis tools? So we have. I've taken a look at the Clang thread safety analysis. It's a feature in Clang that you can annotate your source code to indicate when a mutex must be held or not held. It must be held holding that data member and so forth. But we ran into multiple issues. Turns out the annotations for indicating lock ordering, so acquired before and acquired after, are not implemented. And then it's also impossible to annotate more complicated things like unique lock. because the static analysis tool does not understand conditional locking. We also tried tools like Hellgrind, which is part of the Valgrind suite for finding synchronization bugs. But our binaries were too big, had too many threads, it just didn't work. We also tried instrumenting custom mutexes in the past, but custom mutexes added additional overhead, which was expensive for some teams. Don't pay for what you don't use. And if some teams were OK with additional overhead, TSAN already did this for us. So there was no need to add more instrumentation into mutexes. And finally, we tried to use our eBPF detector tool, the Deadlock Detector, on more types of mutexes. But we ran into issues with inlining. eBPF requires us to pass the symbol that we want to trace, but inline the symbols don't appear in the binary. And for many mutex calls, they're inlined into whatever function that's acquiring the mutex. And so it was impossible to annotate other types of mutexes except for pthread mutex, because it turns out pthread mutex is typically dynamically linked into the binary, and as a result, they can't be inlined. So finally, I have one last takeaway I want to share with all of you. I think we should all think holistically when developing tools, and consider the entire life cycle of the software we're managing, beyond just development and running in production. For each phase of that life cycle, where are the gaps in tooling, and how can we build the appropriate tools to fill those gaps? And if we think in this mindset, we can build much better and more comprehensive tools that improve the end-to-end developer experience. So thank you. These are all the tools I mentioned, and if you check out my poster outside, the QR codes will take you to these links as well. Questions?
Do you have any experience doing this kind of deadlock detection on code running outside of servers, like on embedded devices?
At Facebook, we don't, at least from my experience, we don't. I haven't touched many embedded devices, so I do not.
Or even just mobile devices, you know, this?
This tool will work as long as, it depends. So for, let's say, the GDB extension, if you're using the NPTL implementation, it will still work. The BPF tool is Linux specific, so it's not going to work on iOS and things like that. So it depends on the platform.
Thanks for talk, very interesting. Also, nice macros. Do you have plans to publish them under some open license so that other people can use them as well?
Maybe. Cool, well, thank you.